called the zodiacal constellations, and this conical-shaped band of light appears in those same zodiacal constellations. And it is really quite distinct from the Milky Way. There's the Milky Way almost perpendicular to the horizon in this photograph, and there's this zodiacal light just above where the sun set a couple of hours earlier. This photograph, by the way, was taken with a fisheye lens. That's why the horizon looks curved. It is produced by sunlight being scattered by dust, little particles, in our solar system. So here's the sun, and it emits different colored rays of light, red, green, blue. Some of them scatter or reflect or bounce off of particles and end up reaching our eyes. Okay, so the green and blue and red ones, but they all kind of merge together. There's no chromatic effect. There's no rainbow effect. They all kind of merge together to produce white light. Most rays, like the ones represented by these white arrows, forward scatter. They just keep on going in the same or about the same direction in which they were going. But some rays scatter a little bit and can reach our eyes, and that is what produces this glow in the direction in which the sun had set an hour or two earlier. Okay? Now, of course, the sun is shining in other directions as well. For example, here's a direction in which it's shining. But since most of the bouncings or scatterings tend to be in the forward or nearly forward directions, these rays don't reach our eyes. Okay? It would be hard for a ray of light to bounce off of a dust particle and reach our eye, because that's a big scattering angle. Most of the rays like to scatter in nearly the forward direction. And that's why you don't see the zodiacal light far from where the sun has set. And you don't see it at midnight or late in the night, because the sun is way, way down below the horizon, and the only light you would see is the light that's scattering from these dust particles far away from the sun, and very little light reaches us from there. The zodiacal light is best seen in February and March in the evening, and in October and November in the morning, because that's when the plane of the sun's motion through the sky tends to make its steepest angle relative to the horizon. Here's a very good example where the angle is very steep. You know, it's nearly perpendicular to the horizon in this particular photograph. During other seasons, the angle might be more shallow. And so there's not enough time for the sky to darken sufficiently before the particles that give rise to the zodiacal light have set below your horizon. But when the zodiacal light is perpendicular to the horizon, those particular particles don't set for quite a while, and so there's a chance to see the zodiacal light. And sometimes it can even merge with the Milky Way above. It's just a beautiful sight. Well, another thing that you can see from a dark sky is the faint tail of a comet. The head of a comet you can see sometimes even from a city, but the faint tail of a comet requires a dark sky. Now, I'll discuss comets more later, but comets are basically dirty snowballs, blocks of or bunches of ice and dust and rock that come from distant parts of the solar system. They come close to the sun, evaporate, and those evaporated gases and dust particles that were liberated from the head of the comet then reflect sunlight. It is this reflected sunlight that forms the long, diffuse tail. So here's a photograph of Comet Hyakutake in 1996, and then the next photograph is Comet Hale-Bopp, which was easily seen in 1997. And the head could be seen even from bright cities, but this faint tail required darker conditions to see. The tail is pushed away by electrons and charged particles and light emanating from the sun. Here's a picture of the sun, and it's very active. It's got lots of stuff coming out of it. And in addition to the light, there are charged particles that come from the sun and push the tail of a comet back. So the tail of a comet points away from the sun. These charged particles emanating from the sun cause another interesting phenomenon, and that's the auroras, the northern or southern lights. They are a truly amazing phenomenon. If you're sufficiently far north or way down south, and you're looking at a dark sky, you can sometimes see faint bands of light with multiple colors, reds and greens and sometimes blues, flickering across the sky. Those are caused by the interaction of charged particles from the sun with atoms in our atmosphere. Let me explain how that happens. First, of course, let me just show some examples. A picture is worth 1,000 words. So if my description of what we see wasn't enough, here's some actual photographs of auroras. And these photographs were actually taken from Nebraska, not even all that far north. They are just stunning. They're produced by an interaction of charged particles from the sun with Earth's magnetic field. Now, the Earth's magnetic field looks like that of a bar magnet. You have a north pole and a south pole, and the field lines look something like this. I'll discuss electric and magnetic fields more when we talk about the nature of light in a few lectures. But it looks something like this. Charged particles come in from the sun, and they interact with these magnetic field lines. They get trapped. Charged particles don't like to move across field lines. They like to move along field lines. So charged particles from the sun get trapped, and they tend to get trapped in certain bands where the magnetic field is stronger than in other regions. These are called the Van Allen belts, and there are two major ones and then an inner one here. In any case, the charge-trapped particles are way out here, far from the Earth. But because they don't mind moving along the magnetic field lines, these energetic charged particles slam into the molecules, and especially into the individual atoms in the thin atmosphere of the Earth. Now, the Earth is a big thing compared to the thickness of the atmosphere. The atmosphere is only about 100 kilometers thick. The radius of the Earth is something like 6,400 kilometers. So the atmosphere is very thin, and the charged particles don't interact with the atmosphere until they are very close to the Earth. But when they're very close to the Earth, these energetic charged particles slam into the molecules, causing the electrons in atoms to get excited to upper energy levels. I'll describe this process more later on. And these excited electrons then come back down. They jump down to lower levels, and they can emit light. And it is that light that manifests itself as the northern and southern auroras. Okay? So you're taking the energy of the charged particles, kicking electrons in atoms up to higher energy levels, then those electrons cascade back down and emit light. And I'll describe this process of absorption and emission later on when we discuss the nature of light. But that's what's happening. So if you look at these auroras, they can change pretty quickly with time, because the number of charged particles streaming along the magnetic fields changes, and the amount of interaction with the atmosphere can change. So here's one photograph, and just maybe 10 minutes later, here's how the aurora had changed. It had changed its structure. Now, on another night, it looks this way, and then a few minutes later, it looks something like that. The different colors, by the way, are caused by emission of light from different kinds of atoms in the Earth's atmosphere. There's nitrogen and oxygen in atomic and molecular forms, and they have various kinds of electronic transitions that produce these lights of different colors. To show you how much the auroras can change in nearly real time, here's a movie of the sky sped up by only a factor of 8, and you can see how much the aurora is changing over a very short time interval. There's also some clouds coming in at the lower left there. On another night, this green aurora, sped up by only a factor of 8, is changing in a marvelous and intricate way. Look at that, curtains of light shimmering with time as the charged particles interact with the Earth's atmosphere. It is a truly marvelous sight to behold. I've seen a good aurora only once when I was in Alaska, and I will never forget it. I want to see more of them, and I envy people who live at far northern and far southern latitudes for whom such phenomena are relatively frequent. Look at that. Oh man, imagine just watching that in the sky. It's just beautiful, just beautiful. Well, you don't have to be way up north or way down south to see an aurora. Occasionally we get lucky, and the magnetic fields allow charged particles to reach the surface of the Earth even relatively close to the equator. If you have a particularly energetic set of charged particles, they can pummel their way through the magnetic field and reach lower latitudes on Earth. So here is a picture of an aurora seen from Greece. Now, Greece is not particularly far north, okay, but here it is, the picture of the aurora seen from Greece. And here's another one seen from Arizona. Again, Arizona is not particularly far north, but occasionally you can see an aurora from Arizona. Let me show you how this happens with the following animation. Here we have the Earth lit up on one side by the sun, and there's the side that's not lit up, the side that's experiencing night. And this band of light here represents the aurora. Now watch what happens if I change the strength of the solar wind, this barrage of charged particles that hits the Earth. If I strengthen the solar wind, the aurora moves south and can be visible from farther south than is the case when the solar wind is relatively weak. So here the solar wind is weak, and the charged particles that are coming in are being strongly trapped by the field and are confined to far northern or far southern latitudes. But if the charged particles are very energetic, they can penetrate down closer toward the surface of the Earth and hit magnetic field lines that bring them to an interaction with the atmosphere at more southerly latitudes, sometimes even as far south as Arizona or Greece. Interestingly, if the Earth's magnetic field were much weaker, the auroras would extend even farther south than they do. And if the Earth's magnetic field were stronger, the auroras would be confined to even more northerly or more southerly latitudes, because a stronger magnetic field is more able to confine the charged particles. If the Earth's magnetic field were very weak, these charged particles would hit the Earth in quite a few places and cause more mutations of cells and things like that. So, you know, the risk of cancer would be greater if the Earth's magnetic field were considerably weaker. Sometimes when photographing an aurora, you get two phenomena for the price of one. Here's an aurora with comet Hale-Bopp in March of 1997 in the same direction of the sky. How great is that? And here's an aurora with a bright shooting star, a meteor, not a star at all, of course, flashing through it. Auroral activity tends to be strongest when the activity from the sun is the greatest. Here is a movie of the sun taken by SOHO, a satellite that observes the sun and obstructs the bright solar disk. You can see that in the corona there's all these charged particles that appear bright streaming out, and that the amount of charged particles changes with time. Occasionally you have these incredible outbursts. There was one just now. And it is these outbursts that send huge amounts of charged particles toward the Earth. Ooh, there was one. Wow, there was another one. And when these charged particles slam into the Earth a day or a few hours later, that's when you get the most vivid auroral displays, because you've got lots of energetic charged particles hitting the Earth's magnetic field and being channeled down to the atmosphere, where the charged particles can interact with the atmosphere. Now, depending on the strength of the solar flare, or coronal mass ejection as they are sometimes called, the delay between the ejection and when it reaches Earth can be from a few hours to a few days. So astronomers, by watching the sun, can actually predict roughly when the next great auroral display will be visible. Finally, it is interesting that auroras can also be seen from space. Space shuttle astronauts often see auroras looking down at the atmosphere of the Earth. And auroras have also been seen on other planets. Here's an aurora on Jupiter, where the magnetic field brings charged particles down to interact with the atmosphere of Jupiter, and also an aurora on Saturn, caused by a similar phenomenon. So I hope this shows you that there are lots of wonderful things to see with the naked eye, as long as you have a very dark sky away from city lights and away from bright moonlight. It's a fantastic sight to look at all these faint phenomena out there without any telescopic aid whatsoever.